In this video, I'm going to demonstrate the basics of what a laser is, and the first place to start is to break down the name. A laser stands for light amplification by stimulated emission of radiation. Now let's delve deeper to further demystify that. First, to describe lasers, we will need to describe light and some of its properties. Think of light as a wave travelling through space. If you have multiple waves that line up, you say they are coherent. Coherence is an important part of laser light that sunlight doesn't have. All the light must have the same wavelength, lambda, and be in phase. When you add two waves that are coherent, you get constructive interference, which effectively increases the amplitude and thus the intensity of the wave. If they are exactly out of phase, you get deconstructive interference. The wavelength is important as it can determine what form of electromagnetic radiation or colour of visible light the laser produces. The graph here shows the electromagnetic spectrum with the visible range highlighted around 400 to 700 nanometers. A basic setup for a laser is two mirrors on either side of a gain material. One mirror is fully reflective and the other is partially reflective. The gain material can be any form of matter composed of atoms with electrons. Most of the electrons are in the stable ground state. As the incoming photon, a packet of light, interacts with the electrons in the material, the energy that the photon possesses is imparted to the electron to promote it to the excited state. This is known as absorption, and the energy of the photon directly corresponds to the wavelength of that light. As another photon approaches the electron, it can perturb the electron, causing it to fall down to the ground state. As it falls, it releases the energy equivalent to the energy gap as another coherent photon. This is stimulated emission because the emission was stimulated by a passing photon. What we don't want to occur in the meantime while waiting for another photon is spontaneous emission. Here the electron falls on its own and produces a photon that might not be coherent with the others in the cavity. A three-level laser can help to avoid this. Again, the absorption phase occurs, but instead of falling back down to the ground state, the electron falls to a metastable state, where it can wait longer for another photon to appear, thus increasing the chances of stimulated emission. You can think of these energy gaps as rungs on a ladder. You can't have the electrons stay between a rung. Unlike most ladders, the space between two energy levels decreases further away from the bottom ground state. Every material has its own energy levels with varying energy gaps, and only some have metastable states. As you can expect, not all materials can be used to make lasers, or at least not as effectively as others. This is due to a multitude of other reasons at the atomic level, such as whether a material has a direct band gap or not. You might already be familiar with materials giving off different colours from secondary school from the flame test. Each material has its own colourful fingerprint that lasers exploit. Back to the cavity. The light is amplified as more photons are produced by stimulated emission than spontaneous. As it hits the partial mirror, some of the light is transmitted through. This transmitted light is what we associate as the laser light. This light can be further directionalized by adding lenses. Now we have the characteristic narrow beam and monochromatic light source. But where does this initial photon come from? There are two popular methods: optical pumping from other light sources or electrically pumping using semiconductor p-n junctions. As current is provided, electrons combine with positive holes, producing spontaneous emission. In semiconductor lasers, a laser is said to laze when the current passes a threshold current and the optical power starts to increase. This occurs once the stimulated emission starts to dominate over the spontaneous emission. The following video is of a bar of semiconductor lasers taken inside the Tyndall National Institute. As you can see in the monitor, the probe is providing the positive electrical connection to one of the lasers. The base it is resting on provides the negative or ground connection. These lasers can be very small, and the black bar contains numerous lasers. The voltage is provided by the box above. Thanks for watching this video about lasers.